Good morning, students. Welcome to this class. We are discussing the second unit, part 2. In last class, we discussed the methods to improve the performance of VCR cycle. We discussed two methods in the last class. That is by introducing the flash chamber in between the expansion valve and evaporator, and also by introducing the pre-cooler or accumulator. These both are used to decrease the size of the evaporator, and pre-cooler is used to increase the lifespan of the compressor and to avoid the liquid flow across the compressor. The pre-cooler is used to only allow the vapor refrigerant across the compressor to increase the lifespan of the compressor and also to decrease the work input to the compressor. Clear? So next, third method, by introducing the vapor heat exchanger. We can improve the performance of the cycle by vapor heat exchanger. This is the third method. Simple saturation cycle with subcooling of liquid refrigerant by vapor refrigerant by introducing the vapor heat exchanger. This is one of the heat exchanger placed. Subcooling of, we know that the subcooling process increases the refrigeration effect. To done that subcooling, we are using the vapor refrigerant as a cooling medium here, because the vapor refrigerant having the low pressure, whenever the low pressure vapor refrigerant having the less temperature than the liquid refrigerant, which are maintained at higher pressure. Let us look at this diagram. This is the compressor. From 1- to 2- is the compression process in the compressor isentropically, and 2- to 3 is the condensation process in the condenser coil. The amount of refrigerant which is condensed is M2. This M2 amount of refrigerant after condensation that will be sent to the heat exchanger, one of the heat exchanger placed between before the expansion valve. And then 3 to 3- is the subcooling process. That is a cooling process by using the vapor refrigerant coming from the evaporator. From 3- to 4- is the expansion process, isenthalpical expansion process. The enthalpy remains constant during this process, 0.3- to 4-. And 4- to 1, as we know that it's evaporation in the evaporator by absorbing the heat from the required space to be cooled. 1 is that this is the amount of refrigerant is M1. M1 is equal to M2 here, because M1 is sent to the evaporator, M2 is sent to the evaporator, and M1 is coming from the evaporator. The flow is remains constant. That's why M2 is equal to M1. The same amount of refrigerant which is after evaporation at low pressure, the low pressure evaporator, that is the vapor refrigerant, will be sent to the heat exchanger, which is used as a cooling medium here. Whenever it is passing through the heat exchanger, it absorbs the heat from the liquid refrigerant coming from the condenser. Here, the heat is transferred in this direction. That is heat absorbed by this liquid refrigerant from this liquid refrigerant to the vapor refrigerant. This is in the vapor state. This is the liquid state. Even it is liquid state, even it is in vapor state, the vapor having the low temperature than the liquid refrigerant because of pressures. Whenever the pressure decreases in the expansion valve, it is at low pressure and it is at higher pressure. When it is in higher pressure, the saturation temperature is also higher when compared to the vapor. So that high temperature refrigerant, liquid refrigerant, rejects the heat to the low temperature vapor refrigerant. It absorbs the heat, and that vapor refrigerant coming from the evaporator will be sent to the heat exchanger. Here, the heat is absorbing by the vapor refrigerant. But after absorbing the heat, it becomes a superheated vapor here. It becomes superheated vapor after heat exchanger. And this liquid is a subcooled. This is a subcooled liquid after heat exchanger. So heat exchanging between these two in the heat exchanger. After superheating, the vapor refrigerant again sent to the compressor, cycle will be repeats. So this is the process. Here only one component which is installed in the cycle, that is a system before the expansion valve, that is heat exchanger, in which the heat exchanging between the liquid refrigerant and vapor refrigerant. There is a cooling of liquid refrigerant by vapor refrigerant here. Clear? We know that the liquid refrigerant leaving the condenser, refrigerant, this is the liquid refrigerant leaving the condenser, is at higher temperature than the vapor refrigerant leaving the evaporator. This is the vapor refrigerant which is leaving the evaporator. This is equal temperature, higher temperature. The liquid refrigerant leaving the condenser can be subcooled by passing through the heat exchanger, which is supplied with the saturation vapor. This is the saturation vapor from the evaporator as shown in figure. In the heat exchanger, the liquid refrigerant gives the heat. Liquid refrigerant gives the heat to the vapor refrigerant. Here, like this, we can subcool the liquid which is coming from the condenser, thereby increasing the refrigeration effect. As we know that already we studied the subcooling cycle. Due to the subcooling process, the refrigeration effect increases. This is the pressure enthalpy diagram for the given schematic diagram, that is by introducing the heat exchanger. 1 to 1 dash is the superheating process that is occurs in the heat exchanger, and 1 dash to 2 dash is the compression process. 2 dash to 3 up to 3 is the condensation. 3 dash up to 3 is the condensation. See, 2 dash to 3 is the up to 3 is the condensation. After this, the liquid refrigerant is passing to the heat exchanger. In the heat exchanger, this saturation liquid is subcooled up to 0.3 dash. This is the subcooling process. This subcooling process is occurs by this vapor refrigerant. By rejecting the heat from this liquid, it will be subcooled, and by absorbing the heat from the liquid, it will be superheated. That vapor is superheated from 1 to 1 dash. Here, so this vapor is heat absorbing and liquid is heat rejecting. Due to heat rejecting, the temperature and enthalpy decreases. Due to absorbing the heat, the temperature and enthalpy increases the vapor refrigerant. Clear? So after subcooling process, the 3 dash to 4 is the expansion valve. That is the throttle valve. After expansion, the 4 dash to 1 dash, 4 dash to 1, up to 1 only, the evaporation. 4 dash to 1 only, the evaporation process takes place. That is heat absorbing process. This is the refrigeration effect done in the evaporator. So 4 dash to 1 is the refrigeration effect. After that, 1 is goes to the 1 dash superheated state by rejecting a heat to the subcooling liquid. So this is not under the refrigeration effect in this case, only for up to 1, 4 dash to 1 only the refrigeration effect. This process is occurs due to absorbing the heat from the liquid only. So it is not under the evaporation process. It is not refrigeration effect. You have to not take the refrigeration effect. 1 to 1 dash is not under the refrigeration effect. Clear? So this is one of the advantages that in this cycle, the subcooling process is taking place. Due to subcooling process, the some amount of refrigeration effect, that is 4 dash to 4, is the refrigeration effect, increment in refrigeration effect. Otherwise, without heat exchanger, the 3 is expanded, the conditioned refrigerant at 0.3 is expanded up to 4. From 4 to 1 is itself is the refrigeration effect in the evaporator. So somewhat we are increasing the refrigeration effect, that is the H1 minus H4 in place of H1 minus H4. We are increasing the that is the enthalpy, that is the increasing the refrigeration effect to the H1 minus H4 dash. A somewhat increases. Increment is done by the subcooling process. So refrigeration effect increases, no doubt. But what about the work input to the compressor? When we compress the vapor refrigerant from 1 to 2, the work consumption is very less. That is, the work consumption by the compressor is less when compared to the compressing the refrigerant which is at 0.1 dash to 2 dash. It's because during the superheating process, the density of the refrigerant will be decreases and the piston displacement volume is increases. Whenever the piston displacement increases, we have to give the more amount of work to compress the same amount of mass. Clear? So whenever the superheating process, the work consumption by the compressor is increases. So here refrigeration effect also increases and also work consumption by the compressor is also increases. So we can say that the COP may increase or decrease depends on these two increments. If the refrigeration effect increases more than the compression work, the COP automatically increases. Otherwise, when the compression work is more than the refrigeration work, that is the refrigeration effect, then COP is decreases. Clear? That is purely depends on the practical cycle. Let M1 is the mass of vapor refrigerant, M2 is the mass of liquid refrigerant. Here, these both are same. T3 is the temperature of liquid entering in the heat exchanger here. T3 dash, temperature of liquid refrigerant leaving the heat exchanger. After heat exchanger, the condition of the refrigerant is subcooled liquid. T1, that is the vapor refrigerant which is entering into the heat exchanger, and the vapor refrigerant leaving the heat exchanger is T1 dash. So this is the one of the fluid and this is the another fluid. Specific heat of vapor refrigerant CPV and CPL is specific heat of liquid refrigerant. These are the properties or particular data related to the refrigerant at different conditions. Now let us take the heat balance across the heat exchanger. Considering the thermal equilibrium of the heat exchanger. Thermal equilibrium means the heat balance equation, that is the heat lost by the liquid refrigerant in the heat exchanger is equal to heat gained by the vapor refrigerant. Because here in the heat exchanger, we are using two refrigerants, two types of fluids. One is the vapor refrigerant, another one is the liquid refrigerant. By heat balance in the heat exchanger, the heat is rejected by the liquid refrigerant is equal to heat absorbed by the vapor refrigerant or heat gained by the vapor refrigerant. These two are equal. So that is M2, that is the liquid refrigerant which is coming from the condenser, specific heat of liquid refrigerant into drop in temperature of liquid refrigerant from 3 to 3 dash. Clear? T3 minus T3 dash. This is the amount of heat rejected by the liquid refrigerant, which is absorbed by the vapor refrigerant, which is equal to M1 is the mass of vapor refrigerant. CPV is the specific heat of vapors into temperature increases during the superheating process. This is the degree of superheating. T1 dash minus T1. Clear? Are you understanding? Here, M2 is equal to M1. As we know that mass of refrigerant coming from the condenser is equal to mass of leaving the evaporator. Since M2 is equal to M1 and CPL, that is the specific heat of liquid is always more than the specific heat of vapor because the liquid having the more ability to absorb the heat. Therefore, specific heat is more for the liquid. Therefore, temperature difference T3 minus T3 dash is less than the T1 dash minus T1. When the CPL is more than the CPV, to equate these two, this must be less than this difference. T3 minus T3 dash will be less than the T1 dash minus T1 because రెండు కూడా ఈక్వేట్ అవ్వాలి. ఇది ఎక్కువగా ఉన్నప్పుడు ఇది తక్కువగా ఉంటుంది. బోత్ ఆ ప్రొడక్ట్ కాబట్టి ఈ CPL ఎక్కువగా ఉంటే ఈ డిఫరెన్స్ అనేది తక్కువగా ఉండాలి. సో T3 minus T3 dash is always less than the T1 dash minus T1. That is, degree of subcooling is less than the degree of superheat. Otherwise, HF3 minus HF3 dash is equal to H1 dash minus H1. This is the enthalpies. In terms of enthalpies, difference in the enthalpy during subcooling is equal to difference in enthalpy during superheating. A little consideration will show that the subcooling increases the refrigeration effect from H1 to HF3 to H1 minus HF3 dash. Actually, without heat exchanger, the refrigeration effect is H1 minus HF3, but after locating the heat exchanger, the refrigeration effect increases to H1 minus HF3 dash per kg of refrigerant as compared with the simple saturation cycle. Here, the refrigeration effect is increases. Also, the work input is also increases because even though the performance is less in this method, whenever that degree of superheat is more than the degree of subcooling, the work consumption by the compressor is increases when compared to the refrigeration effect. Clear? So even though the performance is less, whenever the work consumption by the compressor is increases, COP is decreases. So this can be adopted where the cooling is required. Cooling necessary, where the power is available, our power and easy available, free available, this method can be adopted. Clear? Like this, we can subcooling the liquid refrigerant by using the vapor refrigerant. Similar to that, the fourth method, this is the method to increase the performance, simple saturation cycle with subcooling of liquid refrigerant by not the vapor refrigerant. Previous cycle vapor refrigerant use chestunam, ee cycle emo liquid refrigerant use chestuntam. Liquid refrigerant nikku subcooling cheyadaniki again liquid refrigerant after expansion we will use. Let's look at this cycle. M2 amount of refrigerant will be entered into the compressor at 0.1, which is compressed up to 0.2. 2 to 3 is the condensation. 3 to 3 dash is the subcooling process, similar to the previous case. 3 dash to 4 dash is the expansion process. At 4 dash, we are introducing the heat exchanger. That is, we are diverting the refrigerant at 4 dash. Some of the liquid refrigerant will be entered into the evaporator because the 4 dash having the low temperature liquid refrigerant, low pressure and temperature liquid refrigerant. This liquid refrigerant will be bypassed. That is, the sum of the liquid refrigerant is sent to the evaporator. A remaining amount, that is the sum of the liquid refrigerant, is diverting towards the heat exchanger. From this, let us take that is the M3 amount of liquid refrigerant, which is diverting towards the heat exchanger. This M3 amount of liquid refrigerant having the low pressure and temperature. This low temperature liquid refrigerant is used as a cooling medium in the heat exchanger. This cooling medium is absorbs the heat from the liquid refrigerant coming from the condenser. Due to absorption of that heat, it will be subcooled from 3 to 3 dash. Clear? Again here also the heat transfer from the liquid refrigerant. This is the liquid refrigerant. This is also liquid refrigerant, or it liquid plus vapor after expansion, wet vapor. This liquid refrigerant is absorbing the heat because it's having the low temperature, because it is expansion process takes place. After expansion, we are taking that. Due to that expansion, the temperature will be decreases. The low temperature liquid refrigerant absorb the heat from the high temperature liquid refrigerant. Therefore, the subcooling process occurs here. Okay, this liquid by absorbing the heat, that this liquid is sent to the vapor. That is converted into the vapor again. That vapor refrigerant, M3 amount of vapor refrigerant again mixed with the vapor coming from the evaporator and sent to the compressor. Clear? We are not taking the vapor refrigerant after the evaporator into the exchanger. We are diverting the liquid refrigerant before the evaporator into the heat exchanger here. Clear? So what is the difference between the previous and this cycle means? Here the vapor is formed after evaporator. Due to the vapor, it does not absorb the heat from the liquid. It's having no ability, that is the small ability to absorb the heat. That's why we are taking the liquid. Before the evaporator only, we are taking the liquid into the heat exchanger. It's having more ability to absorb the heat from the liquid refrigerant from the condenser, coming from the condenser. So, ఎక్కువ amount of heat absorb చేసుకోవడం కొరకు ఈ liquid refrigerant నే మనం డైవర్ట్ చేసుకుంటున్నాం. అందువల్ల ఎక్కువ subcooling process occur అవుతుంది. This is the only the difference between the previous and this cycle. Here, M3 is the amount of liquid refrigerant which is diverting at 4 dash, and M2 is the total amount of liquid refrigerant, M2, M3 dash, and M4 dash. At M4 dash, that is the sum of the heat. Liquid refrigerant is diverting, and remaining amount is M1. That is M1 equal to total amount M2 minus M3 is the diverting. So this is the M1. Again, M1 is mixed with the M3 and we will get the M2. Clear? Let us go for the pH cycle or pH chart. The pH chart. 1 to 2 is the compression process as usual. 2 to 3 is the condensation in the condenser. 3 to 3 dash is the subcooling process. This is the subcooling process occurs. But it is not superheating at this place because we are not using this vapor as a cooling medium. We are using the liquid as a cooling medium here. 3 to 3 dash is the subcooling process. 3 dash to 4 dash is the expansion in the expansion wall. After 4 dash, at this 4 dash, we are separating the liquid. Some of the liquid is used as an evaporation process from up to 1. and some of the liquid particles are using the heat exchanger, which is also absorbing the heat in the heat exchanger, converted to the vapor again. At this, both are mixed with each other and compressing in the compressor. So this subcooling process, it is not represented, that is the process 4 dash, which is diverting from the evaporator. This process is not representing on the pH diagram. Only the subcooling process is not representing in the pH diagram. Here we know that the liquid refrigerant leaving the condenser is at a higher temperature than the liquid refrigerant leaving the expansion valve. Expansion valve తర్వాత ఉండే refrigerant తో కంపేర్ చేస్తే కండెన్సర్ నుండి లీవ్ అయ్యే రిఫ్రిజిరెంట్ ఎక్కువ టెంపరేచర్ దగ్గర ఉంటుంది. దిస్ ఇస్ ద హైయెస్ట్ టెంపరేచర్ వెన్ కంపేర్ టు దిస్ పాయింట్. అందువల్ల ఇక్కడున్న లిక్విడ్ రిఫ్రిజిరెంట్ ని సబ్ కూలింగ్ చేసుకోవడానికి యూజ్ చేసుకుంటున్నాం. The liquid refrigerant leaving the condenser at this point can be subcooled by passing it through a heat exchanger, which is supplied with the liquid refrigerant from the expansion valve. In the heat exchanger, the liquid refrigerant from the condenser gives the heat to the liquid refrigerant from the expansion valve. The pH diagram of the cycle is shown in this. Clear? Without heat exchanger, the refrigerant which is expanded from 3 itself, the final point after expansion is 4. From 4 itself, it is absorbing the heat in the evaporator. This much of refrigeration effect will be produced from 4 to 1, that is H1 minus H4 only. But after introducing the heat exchanger, so let M1 is the mass of refrigerant leaving the evaporator, M2 is the mass of liquid refrigerant passing to the condenser, M3 is the mass of liquid refrigerant supplied to the heat exchanger from the expansion valve. This is the diverting amount of refrigerant. Here it is mixed with again, that is the M2 value, that is M1 value here. M2 is the total amount, M3 is the diverting, M3 and mixed with the M1, this is the M1, again the total amount is sent to the compressor. Clear? So M1 plus M3 is equal to M2. Considering the thermal equilibrium of the heat exchanger again. Here we are considering the heat balance equation for the heat exchanger. Heat lost by the liquid refrigerant from the condenser is equal to heat gained by the liquid refrigerant from the expansion valve. That is M2 into HF3 minus HF3 dash. This is the heat amount of heat is lost by the liquid, that is a liquid refrigerant during the process 3 to 3 dash. And M3 into H1 minus HF4 dash, H1 minus HF4 dash into M3 as amount of heat gained by the liquid refrigerant. Here, at this point, liquid refrigerant is converted into the vapor during the heat exchanging process. That's why we are taking this M3. M3 is the total, that is amount of refrigerant which is diverting towards the heat exchanger. From this, we can write M3 equal to M2 into HF3 minus HF3 dash by H1 minus HF4 dash. M2 into HF3 minus HF3 dash by H1 minus HF3 dash, because HF3 dash, HF4 dash are the same isenthalpic process it is. So HF3 dash. Let us take, this is the equation 1. We know that the refrigeration effect are equal to M1 into H1 minus HF4 dash. That is from weight to weight refrigeration effect taking place from 4 dash to 1. That is from 4 dash. This is the 4 dash to 1 is the condition. Refrigeration effect done in the evaporator, but the amount of refrigerant is M1 itself, only M1. So M1 into H1 minus HF4 dash. M1 in place of M1 we can write as M2 minus M3 into H1 minus HF4 dash. M2 minus M3 in place of M3 we can substitute from the equation 1. From this, M2 into H1 minus HF4 dash, it is H1 minus HF4 dash is LCM here, minus M2 into HF3 minus HF3 dash. H1 minus HF4 dash is cancelled in the numerator and denominator. So finally, we will, this amount is, this equation is remains. M2 into H1 minus M2 into HF4 dash minus M2 into HF3 plus minus plus M2 into HF3 dash. Here, M2 into HF4 is equal to M2 into HF3 dash. HF4 dash is equal to HF3 because M2 is cancelled. HF4 dash is equal to HF3 dash. That's why I'm cancelling M2 HF4 dash, M2 HF3 dash. So remaining is M2 into H1 minus M2 into HF3 or M2 into H1 minus HF3. That is M2 into H1 minus HF3. HF3 means HF4. H1 minus HF4. So refrigeration effect M2 into H1 minus H4 only or HF4 only. Clear? So without heat exchanger, the refrigeration effect is same as that of the with heat exchanger. Without heat exchanger, the refrigeration effect is total amount of heat circulating in the system into H1 minus H4 only or HF4 only. But after heat exchanger introducing, the same amount of refrigeration effect is that there's the same amount of we will get M2 into H1 minus HF4 only or HF3. Clear? So work done in compressor is M2 into H2 minus H1. Without heat exchanger also the same amount of work. Clear? Therefore, the power required to the compressor does not change by introducing the heat exchanger, and also refrigeration effect is also not changing. Clear? So since COP, power and RE are the same as that of the simple saturation cycle, therefore this method having only advantage is to reduce the size of the evaporator again by reducing the liquid refrigerant through it. Ikkada em jarugutundi, మనం కొంత లిక్విడ్ రిఫ్రిజిరెంట్ మనం డైవర్ట్ చేసినా కూడా సేమ్ అమౌంట్ ఆఫ్ రిఫ్రిజిరేషన్ ఎఫెక్ట్ ప్రొడ్యూస్ అవుతుంది ఇక్కడ. సో రిఫ్రిజిరేషన్ ఎఫెక్ట్ ని మనం ఇంక్రీజ్ ఆర్ డిక్రీజ్ చేయలేము, బట్ కొంత అమౌంట్ ఆఫ్ లిక్విడ్ ని మనం డైవర్ట్ చేయడం వల్ల కొంత అమౌంట్ ఆఫ్ లిక్విడ్ ఎవాపరేటర్ కి తగ్గిపోతుంది. దాట్స్ వై we can decrease the evaporator size. So in this method also we can decrease the evaporator size without changing COP value by introducing the heat exchanger. Here, liquidation through heater. This is the only advantages in this method. These are the 4 methods to increase or decrease the sizes and performance. Clear? Now let us go for the factors affecting the simple saturation cycling. This is the final stage of the unit 2. Your final stage of the unit 2 here. What are the different factors? There are 2 factors which affect the simple saturation cycle. The suction pressure or evaporator pressure and condenser pressure. Whenever the suction pressure decreases, whenever the condenser pressure increases, the COP. What is about the COP? Let us look. We have discussed in the previous article that in our actual practice, the suction pressure or evaporator pressure decreases due to friction, frictional resistance of flow of refrigerant. In jarugutundi ikkada 4 నుండి 1 కి ఫ్లో అయ్యే లోపు ఎవాపరేటర్ కాయిల్ లో ఆ కాయిల్ లో అంటే పైప్ కాబట్టి అది పైప్ కి రిఫ్రిజిరెంట్ మధ్యలో ఫ్రిక్షన్ డెవలప్ అవ్వడం వల్ల ప్రెషర్ డ్రాప్ అవుతుంది. ఓకే, from 4 to 1 pressure drop takes place. Therefore the pressure evaporator pressure will be decreases. So let us consider a theoretical vapor compression cycle 1 after decrement of evaporator pressure. The 1 to 2 is the compression process, 2 to 3 is the condensation process, 3 to 4 is the expansion process, again 4 to 1 is the evaporation process. This is the theoretical cycle after reduction in the pressure, evaporator pressure, as shown in pH diagram. When the suction pressure decreases from PS to PS dash, initially the PS is the actual cycle pressure. Due to friction, the pressure drop will takes place up to PS dash. So due to decrement of this pressure drop, due to decrease of pressure, what about the performance? Performance మీద ఎలా affect చేస్తుంది? Let us look. It may be noted that the decrease in suction pressure decreases the refrigeration effect from H1 minus H4 to. Initially, the H1 minus H4 is the refrigeration effect. The curve is like this. The H1 dash is less than the H1. The difference in enthalpy decreases. That is H1 dash minus H4 dash is the low value when compared to the H1 minus H4. That is the refrigeration effect. Heat absorption capacity of the evaporator will be decreases whenever the pressure is less. Clear? Increases the work required for the compression. From H2 minus H1 is the initial compression work. H2 minus H1 is the initial compression work per kg, but after decrement in the pressure in the evaporator, H2 dash minus H1 dash is the pressure, that is the work given to the compressor. When compared to the previous case, it is more. H2 dash minus H1 is more than the H2 minus H1. That is, work consumption by the compressor is also increases. Therefore, work is increasing here, refrigeration effect is decreasing. By effect of these two, the performance, that is the COP, is decreases. Since COP of the system is the ratio of refrigeration effect to the work done, Therefore, with the decrease in suction pressure, the net effect is to decrease the COP of the refrigeration system for the same amount of refrigerant flow. We are not changing the refrigeration flow, but simply we are decreasing the evaporator pressure. By decreasing the evaporator pressure, the work consumption is increases, refrigeration effect decreases, thereby COP is decreases. Hence, the decrease in suction pressure, the refrigeration capacity of the system decreases and the refrigeration cost increases. Whenever the refrigeration effect decreases, the work consumption by the compressor is increases, the refrigeration cost is also increases because power is more in this case. Therefore, from this we can conclude that the evaporator pressure must be operated higher pressures. Whenever it operated higher pressures, the work consumption is less and the refrigeration effect increases. Clear? So evaporator must be operated at higher pressures. Let us look at the condenser pressure. What is the effect of condenser pressure or discharge pressure? Effect of discharge pressure. Here we are placing the evaporator pressure is remains same, but the condenser pressure is decreasing, increasing from 2 to 3 నుండి 2' to 3 వరకు increase చేస్తున్నాం. That is a PO to PO dash. Initially PD, it is a discharge pressure. We are increasing the discharge pressure from PD to P dash. So by increasing the condenser pressure, what about the refrigeration effect and the work input? Let us look. We have already discussed that in actual practice, the discharge pressure, condenser pressure is also called increases due to frictional resistance of the flow of refrigerant. Now let us consider a theoretical vapor compression cycle. A theoretical vapor compression cycle 1, 2', 3', 4' and 1. Here, when the discharge pressure increases from PD to PD dash, PD to PD dash increase chesinapudu cycle 1, 2', 3', 4', 1 is the cycle. Increase cheyinapudu cycle entante 1, 2, 3, 4 is the actual cycle. It may be noted that the increase in discharge pressure, discharge pressure increase from PD to PD dash. What about the refrigeration effect? A refrigeration effect actually H1 minus H4 is the refrigeration effect. Somewhat the liquid particle will be decreases and H1 minus H4 dash is less than the H1 minus H4. That is, heat absorption capacity in the evaporator will be decreasing from H1 minus H4 to H1 minus H4 dash. So decreasing refrigeration effect. Clear? What the work input? Previously, 1 to 2 is the compression process up to PS to PD. But by increasing the pressure to PD dash, we are compressing from PS to PD dash. That is, compression work is also increases from 1 to 2 nundi 1 nundi 2 dash variki increases. The work consumption by the compressor increases. So increases the work required for the compression from H2 minus H1 to H2 dash minus H1. From above, we see that the effect of increase in discharge pressure increase cheyadam valla is similar to the effect of decrease in suction pressure. Ikkada suction pressure decrease chesina effect discharge pressure increase chesina effect chupistundi. So same effect as that of the decrease in suction pressure, but the effect of increase in discharge pressure is not severe on the refrigeration capacity. It increase cheyadam valla deen meeda pedda effect em undadu, ante refrigeration effect meeda somewhat less effect than the previous case as that of the decrease in suction pressure. Suction pressure decrease chesinapudu more amount of refrigeration effect anedi decrease avutundi. Clear? So we can conclude that from this theory, by increasing the discharge pressure or condenser pressure, the COP, the performance of the system will be decreases because the refrigeration effect is somewhat decreasing and work consumption by the compressor increasing. The ratio between the refrigeration effect by work consumption is the COP. Therefore, COP will be decreases by increasing the discharge pressure. Clear? These are the two factors which affect the performance. So condenser must be operated at lower pressure, then only the COP is more. The condenser operating at lower pressures. Whenever it operating at lower pressures, the COP performance of the system is increases. Finally, I conclude that the pressure limits, the range of pressure limits, that is the suction pressure and discharge pressure, must be operated as low as possible. Clear? This pressure range must be as close as possible. Then only the COP of the system can be increases. And last topic in the unit 2 is actual vapor compression cycle. Actually, we studied the compression is isentropic, condensation is constant pressure, expansion is isenthalpic, and evaporation is constant pressure. Till now, we studied that theoretical cycle, but actually, this is the actual cycle. 1, 2, 3 is the evaporation process at constant pressure, that is the evaporator pressure PE. From 3 to 4, some pressure drop takes place at the suction valve of the compressor. Then some amount of heat by absorbing the heat, temperature is also increases at suction pressure. From 5 to 6 is the compression. It is neither isentropic nor polytropic, because whenever the isentropic compression takes place, the heat transfer is 0. Whenever the heat transfer is 0, the isentropic process takes place. But during compression process, the heat exchanging between the refrigerant and compressor valve. So heat transfer is not 0. That's why it is not isentropic process actually. Let us look one by one process. 1, 2, 3 is the evaporation. 3, 4, 5 is the suction at the place of suction valve of the compressor. 5 to 6 is the compression. 6, 7, 8 is the discharge valve process. That is the process occurs in the discharge valve. 8, 9, 10 is the condensation in the condenser. 10 to 11 is also in the condenser subcooling process. 11 to 1 is the expansion in the throttle valve, isenthalpic expansion. Clear? This is the actual cycle. So the actual vapor compression cycle differs from the theoretical cycle in many ways, some of which are unavoidable and causes losses. The main deviation between theoretical and actual cycles are follows. These are the 4 main deviations. The vapor refrigerant leaving the evaporator is in superheated state. It is in superheated state in actual practice. The compression of the refrigerant is neither isentropic nor polytropic. It is somewhere 5 to 6 is not polytropic nor isentropic. The liquid refrigerant before entering the expansion valve is subcooled in the condenser. The pressure drops in the condenser and evaporator takes place. During this process, the pressure drops takes place. Clear? These are the deviations from theoretical cycle. Let us do one process by one process, another process. Let us discuss the process 1, 2, 3. 1, 2, 3 means in the evaporator, which will occur in the evaporator 1, 2, 3. This process shows that the flow of refrigerant in the evaporator, the point 1 represents the entry of refrigerant into the evaporator, and point 3 represents the exit of the refrigerant from the evaporator in superheated state. The point 3 also represents the entry of refrigerant into the compressor. Point 3 and compressor look entry point in superheated condition. The superheating of vapor refrigerant from 2 to point 3 may be due to a superheating valla enduvalla jarugutunnante 3 reasons valla. Automatic control of expansion valve so that the refrigerant leaves the evaporator as the superheated vapor. Em jarugutundi ante ఈ ఎక్స్పాన్షన్ వాల్వ్ ఎప్పుడు ఓపెన్ అవుతుందంటే ఇది కంప్లీట్ గా డ్రై అయిన తర్వాత ఇది ఎక్స్పాన్షన్ వాల్వ్ ఓపెన్ అవుతుంది. దానివల్ల కూడా సూపర్ హీటెడ్ కండిషన్ లోకి వెళ్తుంది. పికప్ ద లార్జ్ అమౌంట్ ఆఫ్ హీట్ ఫ్రమ్ ద ఎవాపరేటర్. ఎవాపరేటర్ లో ఎక్కువ అమౌంట్ ఆఫ్ హీట్ అబ్జార్బ్ చేసుకున్న ఇది సూపర్ హీటెడ్ స్టేట్ లోకి వెళ్తుంది. పికప్ ద హీట్ ఫ్రమ్ ద సక్షన్ పైప్. సక్షన్ పైప్ హ్యావింగ్ ద మోర్ టెంపరేచర్ దాన్ ద రిఫ్రిజిరెంట్. ఇక్కడ ఏం జరుగుతుంది అంటే సడన్ గా ఎవాపరేటర్ నుండి సక్షన్ పైప్ లోకి ఎంటర్ అయినప్పుడు, కంప్రెసర్ లోకి ఎంటర్ అయినప్పుడు కోల్డ్ రిఫ్రిజిరెంట్ హీట్ అబ్జార్బ్ చేసుకోవడం వల్ల కూడా అది టెంపరేచర్ ఇంక్రీజ్ అవుతుంది, సూపర్ హీటెడ్ కండిషన్ లోకి వెళ్తుంది. దీస్ ఆర్ ద 3 రీజన్స్. First 2 conditions. These first two reasons to increase the refrigeration effect. But the third one is not involved in the increasing the refrigeration effect. Involved in the increasing the refrigeration effect. In the first and second case of superheating the vapor refrigerant, the refrigeration effect as well as the compressor work is increased. The coefficient of performance as compared to the saturation cycle at the same suction pressure may be greater, lesser, or unchanged based on the refrigeration effect and work consumption. First 2 methods matram, 2 conditions lo refrigeration effect, no doubt refrigeration effect is increases, but in third condition the work consumption by the compressor increases but not refrigeration effect. The superheating also causes increasing required displacement of compressor. The compressor work increase out and load on the compressor and condenser increases. Let us go for the another process 3, 4, 5, 6, 7, 8. from 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. This totally occurs in the compressor. 3, 4, 5 at the suction valve, 6, 7, 8 is at the discharge valve, and 5 to 6 is the compression. Clear? So this process presents the flow of refrigerant through the compressor. When the refrigerant enters the compressor through the suction valve, when the refrigerant enters the compressor through the suction valve at point 3, the pressure falls due to the point 4 due to frictional resistance to flow. ఇక్కడ ఏం జరుగుతుంది అంటే 3 దగ్గర సక్షన్ వాల్వ్ లోకి ఎంటర్ అవుతున్నప్పుడు సక్షన్ వాల్వ్ దగ్గర ఫ్రిక్షన్ డెవలప్ అవడం వల్ల స్మాల్ అమౌంట్ ఆఫ్ ప్రెజర్ డ్రాప్స్ టేక్స్ ప్లేస్ ఫ్రమ్ PE to PS. This pressure drop takes place at the suction valve. After that, enter అయిన తర్వాత actual suction pressure is lower than the evaporator pressure. During suction and prior to compression, the temperature of the cold refrigerant vapor rises to 0.5 when it comes in contact with the compressor cylinder walls. Whenever the pressure drops, after pressure drops, the refrigerant, cold refrigerant, will be entered into the suction pipe of the compressor. Ikkada cold refrigerant hot walls ki touch avadam valla somewhat at constant pressure temperature increases from 4 to 5. Okay, hot walls, compressor walls ఎక్కువ టెంపరేచర్ దగ్గర ఉంటాయి, హాట్ గా ఉంటాయి. ఆ హాట్ వాల్స్ ని కోల్డ్ రిఫ్రిజిరెంట్ టచ్ అవ్వడం వల్ల దాని టెంపరేచర్ somewhat increases from 4 to 5 at constant pressure, suction pressure. The actual compression process, that is it is neither isentropic nor polytropic. The compression process is neither isentropic nor polytropic because heat exchanging process takes place. The actual compression of the refrigerant is shown by 5-6. This is the 5-6 is the actual compression process, which is neither isentropic nor polytropic. This is due to the heat transfer between the cylinder walls and the vapor refrigerant. Heat transfer jarugutundi kabatti isentropic anale. Okay, the temperature of the cylinder walls is somewhat in between the temperature of cold suction vapor refrigerant and hot discharge vapor refrigerant. A cylinder walls ekkada untayante temperature between the cold refrigerant which is entering into the compressor, hot refrigerant which is leaving from the compressor. Around it madhyalo ee cylinder wall temperature untundi. It may be assumed that the heat absorbed by the vapor refrigerant from the cylinder walls during the first part of the compression stroke is equal to the heat rejected by the vapor refrigerant to the cylinder walls. అంటే కొంత టైం వరకు ఇక్కడ కంప్రెషన్ స్టార్టింగ్ లో హాఫ్ ఆఫ్ ద కంప్రెషన్ ప్రాసెస్ ఏం జరుగుతుంది అంటే రిఫ్రిజిరెంట్ కి హీట్ సప్లై అవుతుంది బికాస్ కంప్రెషన్ ప్రాసెస్ టేక్స్ ప్లేస్. ఓకే, రిమైనింగ్ ఆఫ్ ఏమవుతుంది అంటే ఆఫ్టర్ కంప్రెషన్ డ్యూరింగ్ కంప్రెషన్ ద హాట్ రిఫ్రిజిరెంట్ గివ్స్ ద హీట్ టు ద సిలిండర్ వాల్స్ అగైన్. క్లియర్? First part of the compression stroke is equal to the reject by the vapor refrigerant to the cylinder walls. Like the heating effect at suction given by the 4-5, ఇక్కడ ఏదైతే జరుగుతుందో 4-5 హీటింగ్, ఇక్కడ ఎప్పుడైతే కంప్రెసర్ నుండి లీవ్ అవుతుందో డిశ్చార్జ్ వాల్వ్ దగ్గర కూలింగ్ ఎఫెక్ట్ విల్ బి డన్. అంటే కాన్స్టెంట్ ప్రెషర్ దగ్గర టెంపరేచర్ డ్రాప్ అవుతుంది. ఇక్కడ టెంపరేచర్ ఇంక్రీజ్ అవుతే కంప్రెసర్ లకు ఎంటర్ అయినప్పుడు, కంప్రెసర్ నుండి లీవ్ అయినప్పుడు టెంపరేచర్ డ్రాప్ అవుతుంది. బికాస్ హాట్ వాల్స్ ని లీవ్ అవుతుంది కాబట్టి రిఫ్రిజిరెంట్ temperature drop out. Whatever the effect is done at the suction valve, a same effect or reverse effect will be done at the discharge valve. That is a cooling effect. Here, heating effect. There is a cooling effect at the discharge as given by 6 to 7. This is the cooling effect done at the discharge valve. These heating and cooling effects takes place at constant pressures. Due to frictional resistance of flow, there is a pressure drop. That is the actual pressure is PD. is more than the condenser pressure. ఇక్కడ మళ్ళీ డిశ్చార్జ్ వాల్వ్ దగ్గర ఎప్పుడైతే లీవ్ అవుతుందో, లీవ్ అయ్యేటప్పుడు డిశ్చార్జ్ వాల్వ్ దగ్గర స్మాల్ ప్రెషర్ డ్రాప్ టేక్స్ ప్లేస్. అంటే ఫ్లో వల్ల, ఫ్రిక్షనల్ ఫ్లో వల్ల the pressure drop takes place from PD to PC. That means condenser operating at this pressure PC when compared, it is very less, it is a less when compared to the discharge pressure. So after leaving the compressor at 0.8, it will be entered into the condenser. Next process it is. Process 8, 9, 10, 11 is this total process is occurs in the condenser. This process represents the flow of refrigerant to the condenser. The process 8 to 9 represents the cooling of superheated vapor refrigerant to the dry saturated state, initial state in the condenser coil, it is cooled from 8 to 9, then it is condensed from 9 to 10. Clear? 9 to 10. The process 9 to 10 shows the removal of latent heat, which changes the dry saturated refrigerant into liquid refrigerant. That is the phase change occurs during the 9 to 10. The process 10 to 11 represents the subcooling of liquid refrigerant in the condenser before passing to the expansion valve. This is the subcooling process by using a low temperature cooling medium. This is desirable as it increases refrigeration effect and increases the refrigeration effect in a subcooling process per kg of refrigerant flow. It also reduces the volume of refrigerant partially evaporated from the liquid refrigerant while passing to the expansion valve. The specific volume would increase outundi. Subcooling valla ikkada expansion chesina anante ikkada expand chesinappudu specific volume is more after expansion. Clear? The increase in refrigeration effect can be obtained by large quantity of circulating water, which should be at the temperature much lower than the condensing temperature. Eppadi subcooling process occur avutundi ikkada cooling medium water edaithe use chestamo cooling process ki aa cooling water must be less than the condensing temperature. Ee temperature kante far less than eppudaithe use chestamo appudu subcooling process kuda occur avutundi. Okay na? Only saturation point variki cool avakunda subcooling process jaragali ante low temperature water ni manam cooling medium ga use cheyali. Clear? This is a large quantity of circulating water, cooling water, which should be at temperature much less than the condensing temperature. Then only subcooling process occurs. Last process, process 11.1. This is a process 11, isenthalpic process, as we studied in the critical cycle. This process represents the expansion of subcooled liquid refrigerant by the throttling from the condenser pressure. Throttling from the condenser liquid refrigerant by throttling from condenser pressure to the evaporator pressure. Ikkada em jarugutundi expansion process in the throttling from condenser pressure. This is the condenser pressure. From condenser pressure to evaporator pressure, it is expanded isenthalpically. It is as in the same case of critical cycle. So like this, there's many deviations will be occurs in the actual practice, but we are studying a critical cycle, which is a very simplified cycle when compared to the actual cycle. Clear? Let us close this class. I will start a third unit in the next class. That is the it is purely theory. Third unit is completely theory related to the components which are used in VCR system. That is the compressor classifications working, condenser classification working, expansion valves and evaporator classification and their working. These are all theory, total theory part in the unit 3. I will cover this theory part in the next class. Okay, I'm closing this class at this time. Bye. Have a nice day.